Okay, welcome to the last lecture of this year's Hsu Distinguished Lecture Series. Professor Cho is going to tell us about character sheaves on loop the algebra. Let's welcome again Professor Cho.
Thank you, Professor Lee. So my talk today is quite different from the two other talks. So two other talks have been more focused on the orbital integrons, both from geometric perspective or analytic perspective. Today I'm switching to the other side, the representation themselves, so the characters. So I want to discuss what the character sheaves on loop Lie algebras. So this is a joint work with Zhu. So I must immediately say that this is official joint work, but all ideas are due to him, right? So my role is very true, to go around and report about this very nice work. I can say nice work because it's really Zhu ideas. So we start off, a couple of years back when long time ago we've been working together on so-called epipedagogic representations. And at some point I asked him how to construct the kind of obvious construction of the epipedagogic character sheaf. And then we try to prove that it's actually a perfect sheaf. And been struggling for many years. Although the thing that we know very well, but on the known technique doesn't seem to, count in dimension, just go wrong. And then last year he has a sabbatical here. He came to Chicago, and then we kept working together every day. Basically, I just see him doing mathematics, and he came up with extremely beautiful ideas and how to be beyond that. Of course, it's not in work in progress. So that many ingredients have not been put in place, but I believe that the pictures are more or less complete. So, so before coming to define what is character sheaf for loop Lie algebra, let me let me tell you the classical stories about character sheaf and about representations of finite group of Lie type. So, so this theory is very well established, come way back, I don't know, maybe in the 80s, mainly starting by Lustig and Lustig. So if G is a reductive group over some finite fields, and then we try to classify representation of this group, right? G of FQ, like G and F of FQs, and just by inspecting, you know how to do it for G and Len, for example, for G and 2 at least, from what you're sure. So McDonald's postulated there should be irreducible representations, should be roughly put into kind of in series, right? Here called the T theta, where T is a maximal torus of G, so not necessarily split, right? And theta is a character of T. So essentially, for every irreducible representation, you can have theta, or maybe you can have a bit confusion for singular theta. But anyway, so that was been achieved by the work of fundamental work of Lustig. So I assume G split for simplicity. Then the so T is the non-split torus, but the Frobenius action of T and the Frobenius action on the split torus differ by some element in the Y groups. So T is correspond basically to some element of the Y group up to conjugacy, right? So so basically, you want to start with some in the Y group, and you want to construct this representation that they call the R, the famous R phi theta, which is a virtual representation. And every representation, irreducible representation, is going to sit in be a direct factor of this R phi theta. So how it goes is a very briefly sketch, because I think it's really beautiful construction. So you have the so B is G mod B, so the flap varieties, and so you have action of G acting on B time B, and by Brouillard decomposition, you have this is the union of orbit by W, right? You can also define the Y group as this set of orbit and define some kind of group structure on it. And then because you have a finite field, you have the Frobenius action from B to itself. And we define XW to be the intersection of the graph of Frobenius with one of these orbit, right? XW is so that X it belongs to BW. Right. So the thing is that we are already quite close to what we want, because you have something depend on W, right? And of course G acts on this, right? But the action of G on this is not interesting, because it's connected group. It's going to act trivially on cohomology. Yes?
So it's OW on the right?
Oh, it's OW, yes. Thank you. But on this, because the Frobenius, G no longer acts on this, but only G of K acts on this. Right? The discrete, the group of K point. Right? So for example, RC1 is going to be the representation of G of K on cohomology compact support of XW. Right. And for theta, any characters of this, he has been involved, but I don't want to go into the detail, but you can deconstruct L theta, a local system on HW, which may not be defined over K. So this is over K bar. So this may not be defined over K, but nevertheless, G of K act on the A-time cohomology of L theta, and which we, by taking alternating sum, you get to this R theta. Right. So that is how the linguistic construction goes, intersecting the Frobenius graph with the the Brouillard cells, and then let the finite group lead type acting on those, and with the local system is you have a family of representation as predicted by McDonald's, and every irreducible representation occurs in those. And there's some orthogonality when theta is generic, but then there's some confusion when theta went to 1, so they call unipotent representation that kind of it's more confusing. So there's a lot of work. Later work is try to to sort out this confusion with unipotent representation. So for example, there's one aspect is what to compute the character. And I don't give you the formula yet, but there's a formula in the linguistic. But it reduced to the restriction of r theta to the unipotent, varieties. So there's some kind of drop-down decomposition, then it enough to compute the residual to the unipotent, and these are called the green function. So it will happen that green function only depend on t, not on theta. So it's depend on not on theta. So the question is how to compute the green function. Right? This is one of the questions, and that question come out to what this kind of basic question, and that is coming to a very beautiful answer. So the answer here is Springer hypothesis. So very simple hypothesis was the beginning of the theory character shift. Right? So how Springer goes? Springer, I don't know how come this is nice ideas, but he basically tell the following thing. So assume that you have some kind of exponential, the block map that identify U with an nilpotent cone. Right? Assume you have such things. Nilpotent cone. So this inside Lie algebras, and so then you have the duon Lie algebras, which is just a linear duon of G, and basically you pick any element Y in T duo, right? Take Lie algebra of this T, take in the duons, and the orbit of Y, this is co-adjoint orbit of Y. Of course, this has to do with the orbit philosophy, whatever. So this, but it really original in this situation due to Springer. Then, and just a characteristic function of this, and do Fourier transforms, and you should get to the green function. So this is a very nice, not precise, but some assumption. But that is the idea. It should be very simple. The W here give you some torus and some Lie algebras. Just pick any element, maybe generic enough. Right? Take the coherent orbit and do Fourier transforms. The Fourier transform will produce the right green function on the nilpotent cone, and by exponential you get to the green function here. So that was the ideas, right? So of course then the theory here probably reverse time a bit, but then you can say that want to define character shift. On Lie algebras are Fourier transforms of orbiton shift. So orbiton shift, what it is, they are just some co-adjoint orbits, some OY in G star co-adjoint orbit. Regular semi-simple or not, but then you have and K to be some simple pervert shift on OY bar. So equivalent, so it be local system on OY, and then do the Fourier transforms. Okay. Is a character shift. So that is how Lustig define character shift on Lie algebras. You look at the orbit on the dual Lie algebras, and we he called orbiton sheaves, those that support basically on one single orbit or the closure of one orbit, and do Fourier transform, and that should give you the orbiton, the character sheaf, and in fact, this includes this kind of Springer construction. By the way, Springer hypothesis was proved by Kashdan, and so this give a kind of right home for this. I think by this Springer hypothesis. Of course, I mean, here I kind of jump in time, but very much by the same motivated by the same question, how to compute irreducible characters, because the arc theta is irreducible only when theta is very generic, and not some kind of composition series complicated on the theta not. So the question of computing character sheaf is character is still not shown by the construction, and because the idea is the irreducible character should be something from irreducible object, and there should be some I don't know how come some simple perverse sheaves. And this is one of the illustration by this construction, but also the Lustig have also defined the idea of character sheaf. On groups, right? So it's more directly related to characters, and that is the basic example. I'm not going to define it because here the definition is actually more involved than that, right? But there's a very basic example. Is given by the Grothendieck Springer. Resolution of resolution singularity. It's not a resolution, but they call it this way. So, so we have the kind of resolve simultaneously on the closure of adjoint orbit. So we have the G, with tin mod G, and here is G tin that is the space of pair of G and X, whereas G in G and X is in G mod B, and we want that G belong to X be X minus 1, right? So this is a pair of an element of G and Borel subgroup, so that the element belongs to the Borel subgroup. Right? So then this map into, of course, this map to G, right? So for example, if G is 1, then this should be can be the whole Borel varieties, every Borel subgroup. But when G regular semi-simple, then there's worth of n factorials, as many as the Y group Borel sub containing that. So this is kind of alteration. It's not a resolution. And this is probably the most basic construction in second geometric representation theory. Everybody had to learn this thing. So this is the pi is a you call this a small map. Some property on dimension of the fibers, and then they imply that P star of QL is a perverse sheaf. Sheaf by dimension is a perverse sheaf, and which is a mid-on extension with restriction to it a regular semi-simple locus. So as I noticed on the regular semi-simple locus, G tilde regular semi-simple go to G regular semi-simple is a W torsus. Is a finite Etan map whose Galois group is W. So on this locus it have a W torsus and you go decompose representation. They have kind of regular representation, and so this whole thing is this pi star QL, and you have to some kind of conventional shift to make it perverse shift has an axis of W, right? And decomposing. So here and simple constituent are the so-called unipotent character shift. Right. So this gives you so as opposite theta is better to be regular. Here take theta 1 to 1. Then you get this construction, and this will give you the kind of Springer correspondence between Y irreducible of Y group and more or less is the nilpotent orbit and so on. But I just skip that. I just want to give you flavors of how we construct character shift, right? So in the case of Lie algebras, we do the Fourier transform of an orbit, the adjoint orbit, quadjoint orbit, and here we have some kind of Springer resolutions. And actually, it's very similar because if you do the same thing here, if you do the replace G by the Lie algebras, you also have a version of the Springer resolution on Lie algebras, right? By here, just by requiring G to be in the Lie algebras of this instead of B, and then you have the same thing and the same on the same segment preserve. So this then pi of the QL, the sum of nilpotent character shift. And you can see that this is the if you restrict this thing to the nilpotent cone, then this is the original Springer resolution. And if you put us, then it can be checked that if you do the push forward of the n tilde to n, and then do Fourier transform, and then you get this thing. And this is how these two connections are connected to one to another. So again, so this is the construction for group. You apply for G tilde, but then if f of restrict to nilpotent cone, then you still have a semi-small map, and the direct image is still a perverse shift, although it's not supported on the regular nilpotent, but it have a bigger sum. And then the Springer shift obtained is the Fourier transform of this thing. So it's very close with the construction, but now here is a nilpotent orbit instead of the regular semi-simple orbit, as I explained over there. So this, I go to this detail to just to put one of the kind of more technical statement in this framework is the Lustig definition of cuspidal character shift on Lie algebras. So Lustig singled out on this whole family, there was one very special thing that happened very rarely, but it's actually the basic block of the whole theory is called the cuspidon if we have the O and L. O is an nilpotent orbit, and L is on support on O bar, so that the Fourier transforms is still nilpotent. It's extremely rare, right? Usually you go to regular semi-simple, then in this case, that if you have nilpotent, then you go spread on over the groups. But there's some case, you know, n had to be some quadratic function, some very, very, you know, strange condition. Then it appears this kind of very peculiar sheaf called Cuspidal sheaf, and on both sides are nilpotent. So both orbital and anti-orbital in his terminologies, and then Lustig basically had a way to do induction. The whole characters can be constructed out of this Cuspidal character sheaf. All right, I think that is all I had to say about finite group. Any questions? All right, so now you know, of course, for Langland's program, the finite group is kind of toy examples, a toy case. We really want to understand the representation loop G of QP, right? Right. And for nowadays, with you know, the perfectoid and so on, it probably can probably construct character sheaf on this, but you know, it geometrically is much easier to do with the group on the loop-Lie group, right? The group on the formal series in FQ, and it was very tempting to try to you know, to generalize character sheaf on the form theory character sheaf to these loop groups. The question is how to for loop Lie groups. So the progress is very slow, right? Because you know, it's not just because they have infinite dimension varieties, but there's many things that are, for example, you know, in this question, for the very beginning, you know, the rough pictures of how classified are clear, right? By McDonald conjecture, they're given by some torus and some character on torus, and there is called Langland's parameters. It's much difficult, but then also the supercuspidal have the U, JKU construction of supercuspidal representations, and which is really a great work, right? Nowadays, you know that they basically give you on supercuspidal representation by later work by Julie Kim and Jessica Finson. It's some tamely ramified case, right? But it's not obvious at all because this looks very combinatorial. On the data, also quite difficult to remember. It's the U data is called, and how to fit that into these geometric pictures. And that was a question: how to fit to geometrize use data. So this is basically how our work on UA ideas answer to this question, and how to give a geometric construction of JKU supercuspidal representations of characters. But before that, there was something that is very remarkable in work of Kashdan. So the basic idea on Kashdan that I think it was worked out by Boutier, Kashdan, and Warshawski. That they claim that this is one can basically we transpose directly this construction to the case of loop groups. So to make it easy here, well, just to make the generalization more transparent, it's better to divide by G on both sides. So of course G acts by conjugation on this, so we have G mod G, and here we have G tilde mod G as a stack. And you just look at the equation, and you can see this is equal to B mod B. Right. So you can see that the Grothendieck-Springer resolution you have to map from B mod B to G mod G. So you think in that way this become quite transparent to how to generalize this. So you have if you have that G is a group of so let's say of FQ of T, right? Then you have the loop groups who FQ point is G of FQ T. Well, it's some certainty how to define loop groups, but it, at the end doesn't matter really. And then you have the L plus J, the positive loop groups, and the group is values in FQ bracket T. Right? So this is maximum complexity to speak, but then it's probably more important is what is similar to this is Iwahori subgroups. So Iwahori subgroup of so is G inside the L plus of G, so that G congruent to some triangular matrix mod T. Right. So this is called Iwahori subgroup, which is the analog of the Borel subgroup in the finite case. Right. So again, this is the group scheme. This is a scheme, and this is the group in scheme, and that's addition group scheme. It's probably not important for what you do, but so the analog of this is just do the analog of the Springer resolution. Is I mod I going to L plus G, LG mod LG. Right, and it's formally analog, but it's not completely so. For example, this map is not surjective, right? An element is here. Every element, on the algebraic closed field, every element can be triangularized. So you conjugate into some Borels. So here it's not so, right? Because to be conjugated into I or into L plus G, all the eigenvalues should not have poles, right? So it's only this is factorized to some subset of this of some equivalent subset of this called the compact element. So LG compact divided by LG, and so and then this map now look a bit like this, and everything infinite dimensional. So, for example, this is I think it seems quite confusing. I've been thinking about this for a while, but I don't have to say that I don't have very clear ideas. So this is actually the in scheme. This is also in scheme. So an in scheme divided by an in scheme is not a good thing. That's not a thing you want to. But but that is how. But there is a way. So that is what the main input of Buchev-Warshawski. There's a way to say that this map is small. So on the geometric point of this, so when this kind of integer element and if the eigenvalues are distinct modulo t, then the fiber here is the infinite, but it's torsion the five y groups, opposed to the y group here. So then if this map pi, suppose the pi star of QL must be of perverse sheaves in the BKV sense, which is a complicated definition. I don't understand why we have to try to tell you in 5 minutes, but even in half an hour. But in their paper, they give a sense of this statement. Right? It's a perverse sheaf and acted on by W tilde. Right? So this is one of the, this should be one of the primary examples of character sheaf on loop groups. Right? Right? So again, the ideas is very similar to this, but there's a technical difficulties how to make sense a perverse sheaf on this context of loop space divided by loop in scheme divided by in groups. Right? On the dimension it be all right. So this is the original question of when Ziwei and I was been starting working is to look at what's called the epipelagic representation. So this is a good example, but actually it's very far from being any irreducible representation, right? This is it's not a principal series, but it's called integration of the principal series on the whole, right? So it should not be the simplest example, although this is the work that I'm working first. But if you want to look at one irreducible, one supercuspidal, it should be simpler. And then the probably nicest example is just the next one is if you have the I plus. If I plus is the pro-unipotent, of I, and then you have the I plus plus maybe is the commutators. Then this is I plus mod I plus plus. Then you can take some characters onto Q to C star, right? And then you can induce, right? It's kind of generic character, some conditional genericities. And then you can induce a compact induction from I plus to G. To G is a supercuspidal representation, and that is epipelagical representation. So the question is how to construct the character of this geometrically. And of course, if you look at the content, it's actually quite obvious. So we just have the I plus mod I plus map into I mod I and map into LG mod LG, right? And here we have theta give you some local system, and then the push forward on the way, on the pi plus, for example. Then pi plus of this L theta must be a near reducible perverse sheaf in BKV sense. So that is all the original question, right? So we set out to calculate this because just follow BKV strategy, calculate fibers, dimension, and so on. But I don't think that actually it doesn't seem to be doable. In some example it works, but as soon as you go a bit for GN2 it works, but GN3 only some quite big trouble. So it kind of okay for GN2, but then look not promising for bigger group it's true, but it's not the kind of naive strategy is not promising. So then we can come back to when look back to the finite story. So we see that clover shift on group is actually quite, even the definition look complicated, have some categories, and it's not as obvious as transparent Lie algebras, right? So why don't try to do this construction instead of group? And by then we'll be very close, right? So all right, so then we want to define some kind of character shift on instead of group. We want to do character shift on loop Lie algebras. All right, but then think about when you do with we do the a bit of representation periodic groups. It doesn't sound right to take a knock bit and do the Fourier transforms, because the knock bit is a thin set, right? And if it just seems to be measure 0 to do any kind of meaningful Fourier transform, but it can go out of you want to have a function, right? So the idea is you actually have so instead of co-adjoint orbit, we have some kind of a thickening. We really opened of co-adjoint orbit. Of course, invariant thickening, and it should be parameterized by U data. Data look very much like U, and in many cases match with the epipelagic situation, right? All right, so I come to the notion of a polar set. So we are going to define, instead of just co-adjoint orbit, I am going to partition the dual Lie algebra into open set, open and closed set of. Okay, this polar set is so here I just need to notations. Okay. So some notation again. So now G, now K is FQ bar, right? Algebraic closed field, and F is going to be K of bucket T, and now G is the reductive groups. d5 over F, and although we instead you can restrict ourselves to the kind of split groups, but in the construction we can it's going to appear that quasi-split group as well. So we need to, in this case, the quasi-split reductive groups, and by the G0 is the split forms. And we know the basic theory of classification of form is you have this automorphism group of K by the inner and then this is the inner automorphisms, and the quotient is the discrete group on the outer automorphisms. And the form is given by the H1 in those, and here this sequence split, right? And they have H1 in those. And here also because it have this surjective, it have section. And in this case, actually, because of this is a C1 fin, you know that this thing is 0. For C1 fin, the H1 volume connected group is 0. So the form are classified by this H1 inside this discrete groups. So this is just a homomorphism from the Galois group of F into this outer of G naught. So because you are going to be termly ramified, I'm going to just declare that this thing is the same as Z. Limit of the root of unit. All right, so this is the a setup, just setup for groups. So because we do with the duality, and we have to be a bit careful with the duality. So we have F, right, and the dualizing of F is also F dt, right, and then you have the residue map is a map from F dt into K, which is trivial on O dt, and also trivial on the D of F, with F in F, right? So in characteristic 0, it just left one dimension left, and then you decide that the residue normalized by residue of dt mod t is 1. In characteristic P, you do the same, although there may be more codimension, but that matters. But somehow you had to say that this, you can put another scalar here, right? You're not forced to put that dt to t equal to 1. It can be 2, right? So that is useful when you look at f over E, some termly ramified extension, right? And then f is k of t, then E is going to be k of some te. Then you can arrange so that te to the m equal to t, right? And then you have omega of f is f dt. So we contain inside omega of E into E dt. So you want to set up the residue so that to be compatible, right? So this is to be compatible. So in particular here the residue of dte mod te going to be 1 over m, right, to be compatible. So we need to be a bit careful with this. So we can do on the limit, so that f infinity is union of mp equal to 1 and k of t to the 1m. Then you can define also the residue also define on this omega f infinity, so that the thing compatible. All right. So so now when you have a T a torus, over F, and then I have a maximum torus, maximum compact, where this the compact Néron models or the parahoric subgroups. So this is a unique parabolic, so also known as the connected neuron. And so, and then I have the T plus is a pro-unipotent subgroup. Right. So now on the Lie algebras, this is by going to the Lie algebras, I have a filtration of LT. This is the LT plus is going to be L compact of T. So the element compact is the zone in T. And on T plus, I call the L local nilpotent. So I think notation is either like this compact. So compact if in T, and local nilpotent if in T plus. Right? So I can do the same for the dual. So I have the for the duons, and then I have filtration. This is home linear home LT to omega. Then I have this is the T star compact and T star local nilpotent. And I should declare this one is TC orthogonal and this one is T LN orthogonal. Right. So only this is not hard, but here the difficulty to set up things in the uniform way. So of course, when T is split, then you have what you believe it. So TC star is the and T is TO tensor K with F. Then TC star is the TO star OF dt over T. So I'm just get confusing with this. So this might be T O star O F dt. Yes. Then this one is T star O F dt over T. Yes. All right. So now we can come to the very basic definition of polar data. Total polar data. It's going to consist of a pair of T and lambda, where T is a maximal torus of G, right? And lambda is the so this is why it's very close to the finite group case, right? Maximal torus, and lambda is now is an element of the duon, but then have to take some thickening, right? Modulo T star topological nilpotent. So this is topological nilpotent. Which is G regular, which means that for every alpha in root of G, right? So after, that is why we have to do the extension. So over some, you can do the over ramified extension, root defined over ramified extension, then the alpha check of lambda, the alpha check of lambda inside omega f mod omega O is non-zero. That is very important. So we have a lambda, a t, then you take a kind of a polar part, and the polar part is required to be regular. That every root applied to it, you get non-zero, right? And so and then you have a map from have a map from LG to this C, that the C is G mod G, right? And then we have the image Y T lambda, so on, so the LC. So Y T lambda is the image, sorry, this is Lie algebras of this lambda plus T star topological in LC. And then it has Z of T lambda, the preimage in this loop Lie algebras. And this is called a torrent polar set. So those are actually going to elements that are going to be conjugate to some element torus, right? And then we require that the poles are actually regular, apply roots at non-zero. So of course it's easy to check that this is going to cover a large part of the Lie algebra, but not all, right? For example, the remember that toponipotent in the G doesn't belong to those, because when in the torus you're going to get there's no polar part. So you need to introduce more involved notion is the kind of polar set, not necessarily torrent. So that goes as follows. So we have now M is a twisted Levy subgroup. Twisted Levy subgroup, which of course it appears in JKU, which is just by centralized of some torus, not necessarily split torus, right? And then you have the Tm is M mod M there. This is the co-centers of M, and you have the so you can do the same but with this torus. So we have the T star, and of course you have the map from the center of M, the connect component of center of M is this is isogeny, so it doesn't see a difference on the Lie algebra, it's isomorphism. So I can let Tm is that Lie algebra and look at Tm star, and you have the M is going to pair of M lambda, where lambda is going to be leaving this T star by T star M also totally important, and which is G regular. G regular here mean that it this condition d alpha check non-zero for on alpha in the relative root system. So for Levy you have the relative root system. They are just the roots of G when you restrict to this torus and throw away though that becomes zero. That is a relative root system, right? So the roots that are is non-zero on T star M then have to be non-zero on this lambda regular set. Right? So this is the a definition of M lambda for more general have involved with Levy subgroup and some kind of bone spot, but involved only on the center of M, right, so to speak, but have to satisfy the same regularity condition. So apply some kind of relative root to that, have to be non-zero. So this have on this similar notation have Z M lambda. So for example, if you take M to G, then you're going to get some, then there's no more roots, right? And so lambda has to be zero. That means that your M has to be totally nilpotent. All right. So for M equal to G, then this is the set of when M equal to Z. And Z M lambda is G topology nilpotent because the so this is the, and then the theorem here, the only thing that in the paper we actually proved, the other thing are more speculative, that if this is partitioned. All right, I'm running out of time, but this, of course, and then you want to say that character shift in loop Lie algebras is going to be Fourier transforms of some local system or some perverse shift of this. For example, for total, it's going to be just constant shift basically, and then Fourier transforms. For M, it will be more complicated, right? For M equal to G, then there should be a shift will look like the Springer shift in Boutier-Kasdan, Warshawski. Right? So what is, but it is have more evidence enough. For example, for the you can reconstruct basically on the U data from this Toron data. For example, if you right, say, let's look at this case. Let's look at this Toron case. Right. So you have a torus, right, and there's some kind of points, and the point is you can write in degree by degree, right, and you just look at the roots. When you pair with the point, you have some different integers that give you a filtration in the root system, right, and the filtration root system give you a sequence of Levy subgroups, and with the action of the Galois group, that gives filtration of the choose Levy subgroup like in U construction, right? And also the lambda here, you can very well just write as a sum by degree, and a sum by degree they give you the phi 1, phi 2, phi m in the U data. So this data really give you the sequence of choose Levy subgroups and also the phi component in the U data. But in U data there's one missing thing, there is sigma 0, which is the Supercuspidal representation of the first one, right? And that had to come, it doesn't appear in the Toron case. It really appears with the M lambdas, and that is when you have then you have in our construction you have some kind of Lustig Cuspidal shift on the Lie algebras on some Levy part, some parahoric group of some M, and that should correspond to the to the sigma 0 in U data. So anyway, I'll stop here. But somehow it makes us happy enough because we have a lot of things to prove yet. But for example, epipedagogy is quite obvious that the thing works, right? But we immediately to the answer to our question. So we have difficulty to prove that the control is perversive, right? But here become Fourier transform something is obviously perverse. Right? So as long as where this kind of perversity of BKV is preserved by Fourier transform, which likely it is, because any kind of perversity should be, reasonable well behaved should be preserved by Fourier transforms, then that should give it a positive answer to our first questions. But of course, it gives much more to give the whole framework of how character shift or loop leadership should be constructed. Thank you.
Okay, thank you for a wonderful talk. Any additional question? Yeah.
Ziwei and I guess Joshua, they also use this point of view of second category.
Yes.
Like when the classical character sheet is like categorical traits of second category. Is it possible for your work?
Well, I don't quite see it here, but I really want to push this more into the direction of the Springer hypothesis, right? Because in the case of finite group, you have the as lambda here, right? Lambda plays the role of the coadjoint orbit in the case of case, and the coadjoint orbit could give you the green function, right? So in this case, this lambda here should say something about Shalaka germs, right? Because, for example, there should be in the case of finite group, it's kind of remarkable. It's not obvious at all that if you choose coadjoint orbit, regular, intersect with the same torus, then the Fourier transform gives the same thing on the nilpotent, right? And here they should be the same. If you have the same torus, different lambda, those should give you something similar. Maybe the germs on the Fourier transform must be equal to some neighborhood of nilpotent cone.
Any additional questions? Okay, so let's thank Professor Cho.